Hello, Algebra 2 kiddos. Today we are going to study Chapter 11, Section 4. We're still working on probability and we're going to check out some compound events. So here's some of the vocab that is mentioned as you look through your text. A simple event. What that means is that you performed some kind of a probability experiment where there was one single outcome. So for example, maybe you flipped a coin and you got heads, or you rolled a number cube and you got a 2. That is just a single outcome. Today we're looking at compound events. The word compound means more than one. And so when you're doing a compound event, that means that you end up with 2 or more simple events. So you might flip a coin and roll a number cube. Or maybe you'll draw a card out of a deck of cards and then spin a spinner and then flip a coin, okay? You're doing 2 or more simple events. When you're doing more than one event, there's going to be situations where you have things that are called mutually exclusive events. And those are events that cannot both occur in the same trial of an experiment. So the example they gave us is rolling a 1 and rolling a 2 on the same roll of a number cube. If you roll a number cube, you can't possibly get a 1 and a 2 because there is no sides on a number cube that have both a 1 and a 2 on it. So those are mutually exclusive. If you flip a coin, you can't get heads and tails. They're mutually exclusive events. And that's what we're going to look at right away. When you are looking at compound events, what you're doing is you are taking the probability of each thing that you're looking for and you are adding them together. So in the last little description, their example was you cannot roll a 1 or a 2. Well, the probability of getting a 1 is 1 out of 6 because there's one on a number cube that has 6 sides. Plus, well, they said a 1 or a 2. There is 1, 2 on a number cube of 6 sides. When you're adding fractions, top plus top, you would have a 2. Your common denominator would stay a 6. Well, 2 over 6 can reduce down to 1/3. So again, what we're doing is you are adding your exponents or your probabilities together, those fractions. Okay, let's go ahead and look at some examples. A group of students is donating blood during a blood drive. A student has a 9 out of 20 probability of having type O blood and 2/5 probability of having type A blood. It says explain why the events type O and type A blood are mutually exclusive. Well, that's because you cannot have both type O and type A blood. You're not going to go to a blood drive and they're going to say, hey, what type of blood do you have? And you'll be like, oh, well, on Tuesdays it's type O and then on Wednesdays it's type A. You can't have both. You might have type O and you might have type A. Okay, so they're mutually exclusive because there is no overlap. You can't have both. What is the probability that a student has type O or type A? So you're finding each probability separately and then adding them together. Well, type O was 9 out of 20. Plus, type A was 2 out of 5. We are adding fractions. You can't add a fraction unless you have a common denominator. So I need to multiply both top and bottom by 4. My 9 over 20 remains. 2 times 4 is 8. 5 times 4 is 20, so I have my common denominator. When you're adding fractions, common denominator just carries on over into the solution. Add the numerators. 9 plus 8 is 17. And again, we are dealing with probability, so we want to look at that fraction, decimal, and percent. 17 over 20 is 0.85, so there is an 85% chance that when somebody comes into a blood drive that they will either have type O or type A blood. Let's look at another one. Each student casts 1 vote for senior class president. Of the students, 25% voted for Hunt, 20% voted for Klein, 55% voted for Vic. A student from the senior class is selected at random. Explain why the events voted for Hunt, voted for Klein, and voted for Vic are mutually exclusive. Well, there is no overlap here as well. Each student can only vote for one candidate. You can't put two people's names on the ballot. You get to vote for one. So it is a mutually exclusive event. What is the probability that a student voted for Klein or Vic? So you find the probability of each one separately and add them. The probability for Klein, well, Klein was 20%, plus the probability for Vic, 55%. So the probability that you randomly selected a student and it was Klein or Vic, 20 plus 55, that's 75%. This time we have the percentage. If I want to write that as a decimal, it's 0.75. 75% as a fraction is 3/4. Okay, so those are some examples of mutually exclusive. Now you might have some scenarios where there is overlap, and when that happens, it's called mutually inclusive. So here's the example that they gave us. Let's say you're rolling a number cube, and they say, what's the chance of getting an even or a prime number? Well, even numbers on a number cube would be 2, 4, and 6. Prime number, by definition, a prime number has exactly two factors, 1 and itself. So prime numbers on a number cube would be 2, 3, and 5, because those are the numbers that you can divide just the number itself and a 1. So if you look at this, there is an overlap. The 2 is both even and it is prime. So this is it's an inclusive event, meaning that you do have some overlap. Some of the items are part of both of the probabilities. So when that occurs, and here's just an example again, just in case you need to look back at it, even numbers, prime numbers, and then how you go ahead and figure this out. Okay, here is the formula. We had 3 even numbers, right? We had 2, 4, and 6. We had 3 prime numbers, 2, 3, and 5. Because the 2 was counted both times, you have to minus how many numbers were overlapped. We had an overlap of 1 value, so you have to minus 1/6 because 2 was actually counted 2 times, and you can only count the 2 once. So it's the probability of even, the probability of prime. There was an overlap of 1 number, so minus 1/6 to get your probability. So you still add the 2 minus how many items were overlapped. Okay, this says, we're going to go ahead and practice them. Okay, find the probability of rolling a 4 or an even number. So 2, 4, 6. So if I look at this, the probability of rolling a 4, 1 out of 6. There's 1 4 out of 6 sides. The probability of getting an even number, 2, 4, and 6. So there's 3 out of the 6 sides. Minus, there is 1 value that occurred in both looking at a 4 and looking at an even. So I have to minus 1 out of 6 for the 1 value that was counted twice. The common denominator stays. Add the top. 1 plus 3 is 4. Now you subtract 1. So 1 plus 3 is 4, minus 1 is 3. 3/6 reduces to 1/2. As a decimal, 0.5 or 0.50. 50% chance that if you roll a number cube, you will either get a 4 or an even number. Okay, here's the next one. A card is drawn from a deck of 52. Find the probability of drawing a king or a heart. So remember, there is a king of diamonds. There is a king of hearts. There is a king, don't laugh at my drawing, of spades. And there is a king of clubs. There we go. Okay, so we have 4 kings out of 52 plus heart. Remember yesterday when we were talking about cards, there are 13 cards of every suit. That means there are 13 hearts out of 52. Minus, there is an overlap. There is a king of hearts. So the king was counted here and the king was counted as a heart. So there was 1 card that was both a king and a heart. Your common denominator carries. 4 plus 13 is 17. 17 minus 1 is 16. I can divide both top and bottom by 4. Your reduced fraction is 4/13, which is 0.31, there is a 30% chance that if you randomly select a card from a deck of cards, you will either get a king or a heart. Okay, let's look at a couple more just because this is a little tricky as you're getting used to it. Find the probability of rolling an odd number, odd numbers, 1, 3, and 5, or a number greater than 2. So you can't count a 2, it has to be greater than 2. So 3, 4, 5, or 6. So the chance of getting an odd number, there are 3 out of the 6 sides. 1, 2, 3 odd numbers out of 6 sides on a number cube. Rolling a number greater than 2, there's 1, 2, 3, 4 out of 6. Minus, we have some overlaps, the 3 and the 5. So this time I have to minus 2 out of 6 because there were 2 values that were in the overlap portion. Your common denominator stays, so the 6 crosses all the way down. 3 plus 4 is 7. 7 minus 2 is 5. 5 divided by 6 is 0.83, so there is an 83% chance that when you roll a number cube, you will either get an odd number or a value that is greater than 2. Okay, let's look at another one. A card is drawn from a deck of 52. Find the probability of drawing a red card or a face card. Okay, there are 2 suits that are red. Hearts are red, and there are 13 of them. Diamonds are red, and there are 13 of them. So if we are looking at red cards, there are 26 red cards out of the 52. Face cards, remember those are the cards that actually have a face. So jacks, queens, and kings have a face. There are 4 of each of them because there is 1 of each in your hearts, diamonds, clubs, and spades. So there are 12 face cards out of 52. Now what we need to do is try to figure out, okay, how many red cards are also face cards? Well, there would be 2 red jacks because you'd have jack of diamonds, jack of hearts. There would be 2 queens that are red. Same thing, your diamonds and your hearts. There would be 2 kings that are red, hearts and diamonds. So there are 2, 4, 6 out of the 52 cards are both red and a face card. Your common denominator is 52. That carries on over. 26 plus 12 minus 6 is 32. You can divide top and bottom by 4. I'd have 8 over 13 as the reduced fraction. 8 divided by 13 is 0.62, which is 62%. So there is a 62% chance that if you randomly draw a card out of a deck of cards, that the card that you draw will either be a red card or a face card. All right, one more idea for the day. Now this gets a little wild. I kind of like it, okay? You are drawing what's called a Venn diagram. And a Venn diagram is 2 circles that have an overlap. This is how you can show inclusive events. So as we read these scenarios, we're going to be able to find some probabilities that when you just read the problem, it sounds absolutely insane. But by using a Venn diagram and figuring out what the overlap is, you'll notice it's not too bad, okay? Here is example number 1. Of 1,560 students surveyed, 840 were seniors and 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? So like I said, when you read that, that sounds pretty intimidating. There's a lot of different bits of information here. So we're just going to go ahead and kind of dissect it. It says of 1,560 students surveyed. That's the total. So that's going to be our denominator because that is the total amount of students that were surveyed. We're looking at 2 pieces, being seniors and reading a daily paper. So that's what the 2 circles are going to represent. We have seniors and we have reads the paper. Okay, now the sum of these 2 pieces, and the 2 pieces I mean the overlap and the non-overlap. The seniors, there were 840. So if I take this number plus this number, I need to make sure that it's 840. Now this circle, I have part of an overlap and then I have not an overlap. This is the number of people that reads the paper. This has to add up to 630, okay? So right here, this is our overlap. This is going to be the seniors who read the paper. This is going to be the seniors who do not read the paper. They told us that everybody surveyed was either a senior or junior. So the overlap is whoever does both. They're both seniors and they read the paper. So not in the overlap, these would be juniors that read the paper. Okay, so just kind of figuring out what all these different areas of this Venn diagram mean. It says only 215 of the paper readers were juniors. So juniors who read the paper, it's this area. That's 215. Now I can easily find the overlap because this circle has to add up to 630. So 630 minus 215 is 415. So this area right here has to be 415. 415 plus 215 is 630. But now we can figure out what value goes right here because this circle has to add up to 840. Seniors who read the paper, we found that it was 415. So to find out the seniors who do not read the paper, 840 minus 415 is 425. So we have 425 seniors that do not read the paper, 415 seniors who read the paper, 215 juniors that read the paper. Here is the question. What is the probability that a student, there were 1,560 students surveyed, okay, so that's our denominator. What is the probability that a student was a senior? Well, there were 840 seniors, plus, or read the daily paper, 1,560, 630 read the daily paper, minus, out of the 1,560, how many of them were overlapped? There were 415 in the overlap region. That means 415 people were counted twice because they were counted as a senior and counted as reading the paper. So I keep my common denominator, 1,560. If I take 840 plus 630 minus 415, I get 1055. You can divide both top and bottom by 5. My reduced fraction would be 211 over 312. 211 divided by 312 is 0.68. So there is a 68% chance that if you randomly selected a person out of the 1,560 that were surveyed, that you would either have a senior or somebody who read the daily paper. Okay, in case you're thinking, holy crap, that was crazy, we're going to do another one, okay? Of 160 beauty spa customers, that is your denominator because that's the total. So there are a total of 160 beauty spa customers. 96 had hairstyling and 61 had a manicure. So there are your two ideas. Okay, we are looking at people who had a hairstyling and a manicure, people who got their nails done. How many people had a hairstyling? This circle needs to add up to 96. Okay, the two individuals, because this circle represents hair and it tells us 96 had a hairstyling. Nails, 61. So this circle needs to add up to 61 when you do the overlap and the not overlap region because we have to make sure that we have 61 people who had a manicure. There were 28 customers who had only a manicure. So 28 only had their nails done. They did not overlap and get their hair done as well. Okay, this is that overlap region. This is hair and nails. 28 people only had their nails done. So 61 minus 28, we're going to know our overlap. 61 minus 28 is 33 because these two numbers have to add up to 61. But now we can figure out if 33 people got their hair and their nails done, how many people only got their hair done? Well, it's 96 minus the overlap. 96 minus 33 is 63. Once you have all of your values in your Venn diagram, now we can find the probability. What is the probability that a customer had a hairstyling or a manicure? Well, out of the 160, Hairstyling, there was 96. Plus, out of the 160, manicure, there was 61. Minus, out of the 160, what was the overlap? There were 33 clients that did both. Your common denominator stays. 96 plus 61 minus 33, it's 124. I can reduce this by dividing both top and bottom by 4. 124 over 160 in reduced form is 31 over 40. 31 divided by 40 is 0.78, which is 78%. Okay, so that's where we are going to end for 11-4. You are doing a book assignment today. Remember, book assignments, they are still graded on did you try every question, but you will be turning those back into me. So please make sure you have it on a sheet of paper where I can actually see your work and see how you're doing. I hope you had a great time today learning about compound events. Again, as always, I'm thinking about you much and miss you. Can't wait till 11.5. See you tomorrow.